Let us look at another important reaction, that is chemical denudation, that is surface lowering in the Arctic. Freezing, which also produces residual fluids with elevated concentration of dissolved solutes, presumably does not have a significant effect as drying because lower temperatures are involved. That means the freeze-thaw cycles can actually break apart rocks and expose fresh mineral surfaces. So this is the major change which breaks the rocks. Freeze-thaw cycle. Explosive shattering or bursting of boulders exposed to cold air temperatures may occur due to an explosive release of tensional stresses. This may be due to hydrofracturing, thermal shock or ice segregation. Similarly, the high-efficient physical erosion beneath glaciers creates an abundance of reactive mineral surfaces, and the resultant glacier floor is susceptible to rapid chemical weathering because of high microparticle surface areas and amorphous mineral coatings. So these are all the ways by which chemical denudation actually takes place. Chemical denudation means chemical erosion process. So what are the parameters that affect include basal thermal regime, drainage configuration, specific runoff, lithology, relief and elevation. These are all the parameters which affect in a positive way. Low water temperature and limited bioglacial activity reduce solid solution kinetics. In other words, they negatively impact or they reduce erosion. The chemical weathering rate actually depends on when the specific discharge increases, the cationic equivalent weathering rates tend to increase as well, and we also have the atmospheric CO2 sequestration which removes carbon dioxide. So why to study about chemical weathering? Because weathering is one of the most fundamental processes on the earth. Chemical weathering of silicates regulates carbon dioxide by reacting with it. So that is what when we talked about atmospheric carbon sequestration. So the silicate basically regulates the carbon dioxide concentration. Chemical weathering in land leads to release of many essential biochemical elements present in the rock. Similarly, it contributes to exchange of macronutrients such as calcium, magnesium, potassium and phosphate, as well as micronutrients such as iron, manganese and boron to the soil. The dissolved solids carried by rivers entering the sea are a major source of several elements in the oceans. The chemical weathering has an ability to neutralize acids, that is, ocean acidification has been modified by these dissolved materials. The acid may be produced by dissolution of CO2 in water, decomposition of organic matter, uptake of nutrient cations by plants, oxidation of sulfides. So these are all the various chemical weathering reactions. The chemical erosion rate is higher than the rate of physical erosion. So this is the major difference between chemical and physical erosion. Let us look at a small comparison between chemical weathering and chemical denudation. Chemical weathering is a process by which chemical reactions decompose primary minerals and rocks and transfer the products to other phases such as soil, water, clays and biomass. Chemical weathering rates are regulated primarily by minimal surface area, temperature, leaching intensity, that means the availability of water, mineral composition, proton flux, solution pH and chelate concentration. On the other hand, chemical denudation is defined as the net dissolved mineral, that is mass loss, in solution from watersheds and continents with associated transport via groundwater and rivers to the ocean. So how they are moving from one place to another place, that is eroded from one place to another place. Silicate mineral weathering is particular influences the chemistry of oceans and atmosphere by removing calcium 2+, magnesium 2+ and bicarbonate ions in continental runoff to the oceans, where they eventually precipitate as carbonates, thereby sequestering or removing carbon dioxide and buffering atmospheric CO2 levels in the geologic timescales. That means it takes millions of years to happen. So what is the geochemistry perspective of chemical weathering and chemical denudation? The chemical weathering and chemical denudation occur essentially together and at the same rate, functioning to break continents in the planetary scale rock cycle. Biota and soil function as mediating agents for water-rock interactions. Mineral mass passes briefly through soil on its path to oceans. The rooted plants should increase weathering rates via organic acid production and by physically altering soils. The inception of vascular plant ecosystem should have substantially affected atmospheric CO2 levels during the Phanerozoic periods. When we look at the ecosystem ecology perspective of chemical weathering and chemical denudation, chemical weathering generates mineral-based nutrients for growth. Weathering is a key to sustainability in most ecosystems. It is a building process in biocycles operating at ecosystem scale rather than the planetary scale. So that is at the eco region only and not at the entire globe. Biota and soil function as both mediating agent of weathering and as pools where nutrients are stored. Chemical denudation is a distinct process which transports nutrient out of ecosystem in the runoff. That is, it causes nutrient loss. So denudation proceeds at the expense of nutrient retention and accumulation. The acid rain is related to Ca2 plus depletion, that is calcium ion depletion in the northern temperate forest of Europe and America, and calcium dynamics continues to be an interest in forested ecosystems. Chemical weathering and CO2 drawdown, because hydrolytic weathering removes carbon dioxide from the atmosphere, that is, it forms carbonic acid. The CO2 drawdown by hydrolytic weathering of silicate minerals may be accelerated at high temperature. That is a negative feedback with respect to global warming. The role of chemical weathering in climate change over glacial interglacial cycle is less understood because it takes a lot of time. The variation in magnitude of glacially driven chemical weathering associated with the fluctuations in ice extent plays a significant role in carbon cycling on geologic timescales. So what is the cascade effect of change in snow cover? The snow gives insulation cover for vegetation and soil and also is the primary controller of soil thermodynamics. So soil temperature is closely connected to physical, that is permafrost active layer depth, and biogeochemical processes, that is decomposition and greenhouse gas emissions. The change of snow cover leads to warming of permafrost soil around 0.3 degrees centigrade per decade. This warming may lead to increased microbial activity, decomposition rates, and bioavailability of previously frozen soil carbon. So there is a change in the carbon present in the Arctic region. There is ample potential for these changes to lead to release of the greenhouse gases, mainly carbon dioxide and methane. This in turn has the potential to accelerate global warming. So in continuation, what are the cause and effect of snow cover change? A potential decrease in snow-covered area may significantly decrease the surface albedo, which would enhance Arctic amplification. A change in air temperature and precipitation will lead to reduction in snow thickness. A warmer climate leads to earlier spring melt and a shorter snow season. Rain rather than snow is a frequent visitor to northern high altitude, which changes the chemical denudation and chemical weathering. These changes will have a greater impact on the Arctic ecosystems. It may result in modification of vegetation trends like greening or local to regional scale browning. That is, there is a loss of productivity in the Arctic region.